Good morning students. Today we are going to discuss about third colligative property, and that is depression in freezing point. We have done two colligative properties. The first one that we did was relative loading and vapor pressure, and the formula for relative loading and vapor pressure was PA0 minus PS upon PA0 equal to WP upon NE into WA into N. This is the first colligative property that we have done, and this colligative property is known as relative loading in vapor pressure. Now, the second colligative property that we did was elevation in boiling point. We know when we talk about elevation means increase in boiling point. And for that, the formula that we have done was delta PV, which is equal to PV minus PV naught is equal to KV into WD upon NV into WA into 1000, where KV is called anisotropic constant. By using these two colligative properties, we can easily calculate the molar mass of a non-volatile solute. That can be easily calculated. Now, we are going to discuss about the third colligative property, and that colligative property is just like elevation in boiling point. Elevation in boiling point we have in haze in boiling point, whereas today we are going to discuss about depression in freezing point. Depression means decrease. It means when a non-volatile solute is added to the pure solvent, its freezing point decreases. Let us take a simple example. We take water and we take sugar solution. You take these two solutions and put in a freezer of the refrigerator. After 5 minutes, take them out. Which will freeze faster? You will find that the pure water, it freezes at 0 degrees Celsius. It freezes fast as compared to the sugar solution. Now the question arises, why the freezing point of the solution decreases? Because when a non-volatile solute is added to the pure solvent, non-volatile solute which do not form vapors, the freezing point decreases as the surface area of the solvent decreases. So let us discuss about depression in freezing point. Now let us discuss depression in freezing point. This is a graph between temperature versus vapor pressure. We all know what is the meaning of freezing point. Freezing point is the temperature at which the solid and the liquid of the same substance coexist, or we say that they are in equilibrium. So freezing point, when we write the definition, we say freezing point, temperature at which liquid and solid of the same substance is in equilibrium. So this is the definition of freezing point. So we must keep in mind freezing point is the temperature at which the solid and the liquid of the same substance coexist or are in equilibrium. So when we plot a graph between temperatures versus vapor pressure for the pure solvent, the graph is something like this. This is the temperature at which the solvent freezes. This temperature, the solvent freezes. This temperature is written as TF naught. But when a non-volatile solute is added to the pure solvent, this solution freezes at the temperature lower than TF0, and this is called TF, and TF is called freezing point of the solution. So we have seen that when a non-volatile solute is added to the pure solvent, the vapor pressure of the solution decreases and its freezing point further decreases, and the freezing point comes to be TF. So this is the graph for the solution. This one, and this one represents the pure solvent. The difference in the freezing point of these two is represented with delta TF. So delta TF is known as depression in freezing point. So experimentally it has been found that the depression in freezing point, it is directly proportional to molarity of the solution. So let's move further. Delta TF is directly proportional to M, and we all know small m means molarity. Therefore, delta TF is equal to Kf into M, where Kf is called cryoscopic constant. The cryoscopic constant is equal to delta TF, that is depression in freezing point, if the molarity of the solution is 1. So, if the molarity of the solution is 1 or unity, we say depression in freezing point is equal to cryoscopic constant. Now we put the value of delta TF and let us find how to use this formula to calculate the molar mass of a non-volatile solute. Now, delta TF is equal to Kf into M. M is molarity, so it is Kf into Wb upon Mb into Wa into 1000. This is delta TF. Keep in mind, delta TF is equal to TF0 minus TF. This is depression in freezing point. By using this formula, molar mass of a non-volatile solute can be easily calculated. So this formula, that means delta TF equal to Kf Wb into 1000 upon Mb into Wa can be used to calculate the molar mass of a non-volatile solute which is added to the pure solvent to decrease its freezing point. Now, question comes in mind, how we can see that delta TF is a colligative property. Now, for that, look at here. Delta TF is directly proportional to molarity, and molarity in turns depends upon number of moles. Since delta TF depends upon number of moles, hence it is a colligative property. So this one is the third colligative property, that is depression in freezing point. Now we are going towards a most important last colligative property, and that colligative property is called osmotic pressure. The fourth colligative property is osmotic pressure. Before doing the osmotic pressure, we must understand what is osmosis. Before doing the osmotic pressure, we must understand what is the meaning of osmosis. Osmosis, the phenomena of movement of pure solvent from a region of low concentration to the higher concentration through a semi-permeable membrane. Here I am using a word SPM. SPM is called semi-permeable membrane. This semi-permeable membrane is of two types. One artificial and second is natural. What is the meaning of SPM? Semi-permeable membrane. Semi-permeable membrane it allows the solvent molecules to pass through it. It do not allow the movement of the solute particles. Now let us take a very simple example. You take egg. We take one egg, dissolve in HCl, remove its outer layer. Hard layer of calcium has been removed. When we place this egg in a pure water, and placed in pure water, you will find that it swells, its size increases because the water, it moves from a region of low concentration to the higher concentration. The water moves from low concentration to the high concentration through the layer of the egg. That layer is called SPM, semi-permeable membrane. And this phenomena of movement of pure solvent from low concentration to high concentration is called osmosis. Now, if we take again the same egg from the pure water and we place it in a salt solution, you will find that the size of the egg decreases. It means the egg gets shrinks. The reason is very simple. Outside the concentration is high, whereas inside the egg the concentration becomes low. And we know in osmosis solvent moves from low concentration to higher concentration. In this way, the size of the egg shrinks. So this is known as osmosis. So what is osmosis? Osmosis, phenomena of movement of pure solvent from a region of lower concentration to higher concentration through SPM, semi-permeable membrane. So this is called osmosis. Keep in mind osmosis phenomena. Now, there are two types of semi-permeable membrane. One is natural and second is synthetic. The natural membranes are just like outer layer of the egg. Then we have animal bladders. And synthetic, when we talk about synthetic SPM, one is natural and second is synthetic. We have potassium ferrocyanide. We can even use copper ferrocyanide. These are artificial semi-permeable membranes. So I hope you all have understood the concept of osmosis. Now, there is one very important question which comes in mind or which comes in exam is osmotic pressure. We have done osmosis. Now, what is the meaning of osmotic pressure? Let us discuss osmotic pressure. Osmotic pressure is the external pressure applied on the solution side to just prevent the osmosis. It means due to osmosis, the solution, it exerts some of the pressure, and the external pressure which we apply on the solution side to just prevent the osmosis called osmotic pressure. Let us take a simple example. Let us take a container which has SPM, that is semi-permeable membrane, separating the two solutions. Here we take water, pure water. And here we have cap of piston, frictionless movable piston. On this side we have higher concentration. We call it solution. We will find that due to osmosis, pure water moves from lower concentration towards the higher concentration, as a result of which the level of the solution increases. It starts moving the piston, or it pushes the piston in the upward direction. Now, we want that the piston should not move, or the process osmosis just stops. We have to apply external pressure on the piston. So this is the external pressure applied on the piston, so that there is no movement of pure solvent from lower concentration to higher concentration. This pressure is called osmotic pressure, or it measures osmotic pressure. So what is the definition of osmotic pressure? Osmotic pressure is the external pressure applied on the solution side to just prevent the osmosis. So let us write the definition of osmotic pressure. So osmotic pressure, this is external pressure applied from solution side to just prevent the osmosis. Is called osmotic pressure. Experimentally, it has been found that the osmotic pressure, it depends upon two factors. It depends upon concentration as well as it depends upon temperature. The osmotic pressure is represented with pi. First, pi directly proportional to concentration, which is called Boyle's Banov equation, and second, pi directly proportional to temperature, which is known as Banov-Charles equation. So we have seen that, now we can see there are two values, pi directly proportional to C, Boyle's Banov equation, and pi directly proportional to temperature is called Banov-Gay-Lussac equation, or Lussac's equations. On combining these two equations, we get pi directly proportional to Cp. So pi equal to CRT. We all know what is R. R is called gas constant. So pi equal to, if we substitute the value of concentration, concentration is defined as number of moles per unit volume. So N upon V into RT. Since pi depends upon number of moles, hence colligative property. So we have to keep in mind osmotic pressure is a colligative property because osmotic pressure depends upon number of moles of the said unit. So pi equal to N upon V into RT. Now this formula can also be used to calculate the molar mass of a non-volatile cell unit. How we apply this formula to calculate molar mass of non-volatile cell unit? Let's substitute the value of N. We write it NV, number of moles of non-volatile cell unit. And what is the formula? Pi equal to number of moles can be written as given mass upon molar mass into RT upon V. So molar mass can be easily calculated by applying the formula WV RT upon pi V. By applying this formula, we can easily calculate the monomass of a non-volatile solute which is added, so that we can easily measure the osmotic pressure of the given solution. So we have to keep in mind the formula. Pi equal to Wv upon Mv into RT upon V, where R is a gas constant, T is absolute temperature. Now, there is another important topic. We have two types of osmotic pressure solutions. One solution is called isotonic solution. They are saying what is isotonic solution? Isotonic, as from the name it is clear, tonic. Tonic means osmotic pressure. So, isotonic solutions are those which have same osmotic pressure. Those solutions which have same osmotic pressure are called isotonic solution. Then we have hypotonic solution. This solution which has lower osmotic pressure. Solution with lower osmotic pressure called hypotonic, and the third is hypertonic. Those solutions which has higher osmotic pressure. Those solutions which has higher osmotic pressure are called hypertonic solutions. Now there is one very important question, or we can say it's a fact. Question comes in board: what happens to the blood cell when it is placed in NaCl solution having 0.9% concentration? Now keep in mind, 0.9% NaCl solution is isotonic with blood cell. It means when we place a blood cell in 0.9% NaCl solution, it neither swell nor shrink. But when the concentration increases from 0.9%, the size of the blood cell decreases and it bursts. Similarly, when the concentration decreases from 0.9%, then the blood cell it swell and get ruptured. So with this we have done all the four colligative properties. Tomorrow we will discuss about the numericals based on these two colligative properties. One, depression in freezing point, and the second one is osmotic pressure. Thank you, and keep revising these concepts. Keep solving the numericals.